We talked about evidence for the young Earth. Well, also the evidence why they believe that it's old. Radiometric dating, well, that's not too good. The geologic phenomena is what I really like to talk about. And from that, I think we can see good evidence, as even many of the paleontologists today, perhaps most, would acknowledge. The individual rocks happened rapidly. Dunbar and Rogers, as we saw a moment ago, says there's very good evidence that the individual beds accumulated rapidly. And he's not saying that because it's fun to say for him, but because of the kind of evidence that we were looking at. But you ain't seen nothing yet. Let's look at Willow. This is an amazingly preserved dinosaur, North Carolina State University, with heart intact. Now, we see some of these programs where they're trying to transplant the heart, and they get in the helicopter and they put the thing on dry ice and they run across the roof of the hospital and dash into. Because why? It deteriorates quickly. But this became a rock before the heart deteriorated. Here in the museum sign, what are the odds of finding a fossilized dinosaur heart? The seemingly impossible has occurred within the 66 million-year-old skeleton, which they have no doubt about, of course. Here we see the picture of the thorax, the chest, with the heart intact. And they've done CAT scans and all kinds of examination. This shows the clavicle, the collarbone, the neck bone here, but right here in the center is the heart. And there's the right ventricle and the left ventricle of the dinosaur heart. And in the center, the interventricular septum, all beautifully preserved. Now, how long did it take this? Now, this is not a heart. This is a rock. And how long did it take to form? At the rate of 2,500 years, it would cover a hair. I mean, this is idiocy. You just don't have words strong enough to describe the nonsense here. From National Geographic a few years ago, here's a mummified duck-billed dinosaur, 90% covered in soft tissue, stomach contents so well preserved, researchers can tell what he had for his last supper. But, of course, he was covered at the rate of 2,500 years to cover a hair, 30,000 years a foot. But it gets worse. We're looking here at dinosaur blood cells from a T-Rex. Blood cells, of course, last millions of years. Had to be 65 million. And this was what was written in Science Research News back in '93. Round, tiny, nucleated, they were threaded through the bone like red blood cells and blood vessels, but blood cells in a dinosaur should have disappeared eons ago. It was exactly like looking at a slice of modern bone. The bones are, after all, 65 million years old. How could blood cells survive that long? And, of course, the author is just asking the question, but there was a furor, and the lady that wrote this lost her job, got in serious trouble. But she decided to do more work, and she persevered and got her doctorate. She is now Dr. Mary Switzer at North Carolina State University, and has continued this investigation and has found some amazing things published just fairly recently. Now, her colleagues will say this is impossible, but she says here it is. This is the squishy, gushy, soft tissue from a T-Rex. Now, I was writing her about this particular specimen, and she acknowledged our current theories do not account for soft tissue and cellular preservation. Never in my wildest dreams would I have predicted what we found. It's certainly not anything like what you see in the textbooks or according to the theories. It was reported in Discover in April of '06, and she was interviewed. She said, I had one reviewer tell me that he didn't care what the data said. He knew that what I was finding wasn't possible. And it's not. If it's 65 million years old, he's absolutely right. I wrote back and said, well, what data would convince you? And he said, none. Very scientific. And he's telling the truth, believe me. The evidence doesn't matter. Since then, she's just found a wealth of material in the Tyrannosaurus rex bones, the gushy, stretchy, soft tissue, blood cells, blood vessels, and it is not possible for it to be 65 million years old. The conclusion is these dinosaur fossils cannot be old. It's impossible. And, of course, the evolutionist knows that. Now, let's think about that for a moment. I mean, it won't hurt. Let's try it. Okay. If the fossils in the layers are formed rapidly, and from the things we've looked at, the jellyfish, the little stretchy, gushy blood vessels, if the fossils in the layers are formed rapidly, wouldn't it necessarily follow that the layers that the fossils are in followed rapidly? I think you have to reach that conclusion. And so when we're looking at all of these layers, all of which have the kinds of fossils we're talking about in them, then we're talking about something that did not take millions of years. Well, then where is the time? And even the geologists today are saying, well, yes, we know the individual layers formed rapidly. Okay, if you know that, where's all this time? And they have an answer today. They say it's in between the layers. And I say, you mean where there is no evidence? And that kind of slows them down a little. But it's worse than that because there's evidence in between, as we'll see. But let's let them say this for us. Here's, at the time, president of the British Geological Association, in his book, New Catastrophism, president of the British Geological Association says, we cannot escape the conclusion that sedimentation was at times very rapid. You look at the trees, he referred specifically to the polystrate trees. But at other times, he says, there were long breaks in the sedimentation. Now, what's the evidence for the long breaks? Well, that's where there is none, but he's confident that it's there, admitting it looks uniform and continuous, but we know. I mean, after all, we know dinosaurs were 65 million years ago, and so there have to be breaks. It doesn't look like it, but we know there had to be. And when you look at the rocks, yes, it looks uniform and continuous. And you can tell when it's not. You have what we call bioturbidation. If a surface is exposed for any period of time, for less than a year, you've got clams burrowing, you've got worms burrowing, you've got plants sending down roots, and they just plow up the surface, and they don't leave these smooth, straight lines. They're eroded and they're plowed under or over or within. But what we're looking at here is straight and level and smooth with the interfaces perfect in many instances. But he's sure it's there somewhere. He says the geological record is constantly lying to us. You don't listen to it. It pretends to tell us the whole truth when it's only telling us a very small part of it. Nowhere in the world is the record or even part of it complete. He imagines something much more than is there. It may seem paradoxical to me, but the gaps probably cover most of Earth history. And so he's basing his conclusions mostly on what's not there. I think you ought to base your conclusions on what is there. Is that better science? It was during the breaks that most of the events probably occurred. He has faith in that. It's not because of the evidence, but it's the lack that he depends on. It's the gaps that really matter. Now that just boggles my mind that a scientist could say it's not the evidence that matters, it's where there's not evidence. That's what matters. And that's where I'm going to tell my story, and that's where most of it took place. The individual rocks, yes, they happened rapidly. Well, we've got to get time in there somewhere. It's in the gaps. That's where most of it happened. Well, let's look at some of the gaps. Here's the Coconino Sandstone and the Hermit Shale down toward the base of the Grand Canyon. And here's the interface. Now, this is it looks uniform and continuous, but according to their dating of these rocks, there's at least 110 million years in between these two layers. That's what the geologic column says. Well, there was erosion for 110 million years, which left a straight, perfectly conforming line. Flat, smooth surface, not bioturbidated, not eroded. That takes a lot of faith, doesn't it? That's certainly not what it looks like. And when we look at the canyon, that's the way it looks from one end to the other. It looks smooth and straight at the contact lines, not like there was bioturbidation, not like there was erosion. It looks like one continuous deposition. A year-long series of catastrophes, I think, would do an excellent job of explaining this. Consider the contact lines. Where there is no evidence? Well, no, there is evidence at the contact lines. Here's one of them, and we're looking at little bird tracks. And the little bird walks along in the mud, and that's going to stay there for 110 million years before the next cover comes over. Even if you did form it rapidly, and you've got the track in the rock, like in the concrete, then what's going to happen in the tens of years if this is exposed? You've got to have it covered quickly. The next one has to come quick. This is not merely a lack of evidence, but there is evidence at the interface. The most common feature in between the layers are the ripple marks. And it's been said that if you follow any bedding plane far enough, you'll find ripple marks. They're that common. Schrock, in his rock book, as we called it, Schrock's rock book, because they were one of the commonest, most widespread of original sedimentary features, ripple marks are preserved in conglomerates, sandstones, siltstones, clastic limestones, dolestones. There are no rocks that don't have ripple marks. Many examples have been described from rocks of all ages, I would say environments rather than ages, but all kinds of rocks all over the world have got ripple marks. This is from down at Glen Rose with the dinosaur tracks, which, by the way, are not going to stay there for millions of years. Any tracks are going to be eroded quickly, usually with the next rain, but ripple marks here are beautifully preserved. Now, the host layer that forms these ripple marks had to be formed rapidly in order to preserve them. These little ripple marks move from minute to minute as the water runs over the sediment at the bottom of the stream. But this is frozen in the rock. Then, once it's frozen in the rock, if it's not covered, it'll be eroded within tens of years if that surface is left exposed. And so the next layer had to be rapid to prevent erosion. And so the host rock has to be quick, and the one on top of it had to be quick, and the one on top has ripple marks on top of it, and so it had to be quick, and the one on top of it had to be quick to preserve it, and so on we go up the column. Virtually all layers have ripple marks at the bedding plane, which says virtually all of these layers have to be rapid, one after the other, to form and to preserve what's at the interface, where there is good evidence. It's not just a lack of evidence, which is bad enough. There is evidence, and it's very negative when you look at the interface. But let me show you something that's a real killer. Now, you got to think a little bit. But this refutes, I think, conclusively, the picture that we're typically presented in the geologic column. Here's the Red Wall Mississippian, the most dramatic layer that you see when you go to the canyon. Mississippian is almost halfway up the geologic column. The lowest layer in the column is the Cambrian, and the Muav limestone here is Cambrian. So here's the lowest layer, Cambrian. You skip the Ordovician, the Silurian, the Devonian, and get up to the Mississippian. There's almost 200 million years that are missing between the Red Wall and the Muav. Now, how do you skip 200 million years? Well, if you've got deposition in one place, you've got to have erosion somewhere else, and so there was erosion here during that period, which left these straight level lines that you can trace for 300 miles up the canyon. But that's not the only challenge, just the fact that it's missing with a straight line in between. As you look above the Muav, you see this thin piece of red wall, but then above the red wall, you see more Muav. Now, you skip forward 200 million years, and then you come back 200 million years in order to get some more Muav, and then you go forward, and then you go backward, and then you go forward, and then you back and forth, skipping 200 million years, backwards and forwards and backwards and forwards 8 times. Ain't no way. It's interbedded, and the fundamental rules of stratigraphy indicate if it's interbedded, it must be contemporaneous, even though the geologic column says it's 200 million years apart. It can't be. It is absolutely impossible. It looks continuous without the bioturbidation. It is continuous. It cannot possibly be millions. These two cannot possibly be 200 million years apart. They are interbedded. And so geology fails. When you study the rocks, you know this story is a tale that does not fit the facts. But how do you, can you really envision forming all of these layers quickly? Well, let's look at it happening. Mount St. Helens is a demonstration of what happened. 1980, it blew its top, and the pyroclastic cloud went across the countryside at almost 200 miles an hour and laid down sediment here, forming Spirit Lake, the trees across the top. And then when Spirit Lake broke through the temporary dam, it eroded down through the newly laid sediment, leaving this huge canyon up to 600 feet thick, that is deep. Here's another picture, 600-foot cliff over here. And this is rock now. And this little trickle down at the bottom is what cut this big canyon. You think? I don't think so. It was a whole lot more water that eroded that canyon. And that reminds us of another story that's being told. But we look at the walls of this canyon, and you see these finely graduated, laminated layers that happened one afternoon at almost 200 miles an hour. We were told in class, you count these little layers, it's at least a year per layer. Probably more, but at least. And so you had the job of going out and counting the layers and seeing how many thousands of years were represented here. 600 feet of this happened in less than 3 months, most of it in one afternoon. And then with the erosion through that, you have a canyon that looks for all the world like the Grand Canyon. A 40th scale Grand Canyon, the same side slumping canyons, the same geomorphology. It reminds me of the cartoon that a friend of mine drew. This million-year-old canyon was formed by Mount St. Helens in 1980. Yeah, that's the story. But it's also the demonstration of what I believe happened. And we can see that. Did you see it forming slowly? No. You saw it forming rapidly, which is better science. We've all seen the speleotherms in the caves, the stalactites and the stalagmites, and heard the spiel. These are hundreds of thousands of years old. I was taught in my textbook there at Indiana University, it takes at least 100,000 years to form 1 cubic inch. And at that rate, it would take a long time to form these tall speleotherms, this one from North Alabama. The previous one from near Bedford, Indiana, which is not too far from where this picture was taken. This is the George Rogers Clark Memorial near Vincennes, Indiana, on the banks of the Wabash River, a clay bank here. And the limestone here was quarried from within just about 3 miles of where that slide before last was taken. Same limestone, water percolates down through the cracks in the rocks, and in the basement we have speleotherms, just like we do in the caves. The building, when these pictures were taken, was 40 years old. It's a very interesting story how these pictures were taken, because they would not allow anyone in, even the National Speleological Society. We had to threaten to cut their funding off through the legislature, which they then responded to. I think I could have had one of those columns when I finally showed up, but I did get in, and there were 5 of these columns, and they just didn't want people to know what was going on. In New Zealand, a friend of mine sent me this picture of the zinc mine. Notice the people over here in the lower right-hand corner. This was a 30-year-old tunnel with a concrete bunker there across the middle. Obviously takes hundreds of thousands of years. I have an associate who is referred to here in Arizona Highways, Jerry Trout, and a good friend who works with Jerry Trout down in South Texas, Sonora Caverns. And here they report, while some believe beautiful icicle-looking stalactites take years to form, Jerry Trout, cave specialist with the Forest Service, says that through photo monitoring, he's watched a stalactite grow several inches in a matter of days. And his associate told me of being there when they set up the camera on time-lapse photography, and the thing grew past the lens and out of the frame in a month, and so they had to back up and do it quicker. It's just not so that it takes millions of years. Here's a scene from Carlsbad Cavern. Of course, there are a lot of bats flying around there, and one of them got trapped in a stalactite. Real slow bat. We're looking here at a boot. We're familiar with that here in Texas. This is from out in West Texas. Inside of it is a petrified cowboy leg with flesh, including bones, that are fossilized. Some bad things happened to him. The bottom of his foot is crushed. We found the boot. Actually, this is part of his femur down there, slammed into the boot. This is all we know about him. But when we look closely at these bones, in fact, we've taken them to a hospital here in Dallas to be CAT scanned. They tell us this is actually a part of the festered part of the wound that is now rock that's preserved in the cowboy boot, which was made out of T-Rex skin. You think? It was actually made by the J. Letty Boot Company, and was made in the 50s. We have identified it from the stitch pattern. When the CAT scan came back, they had to have a name on it. It said, "Unfortunate Cowboy." We prefer to call him the Limestone Cowboy. One of my favorite fossils was from New Zealand. This is not a hat. This is a rock now. But obviously it doesn't take a long time. Some of you have seen the teddy bear that's petrified in the artifact room. When you look at the rapid and continuous nature of the fossil record, from the polystrate, that is through many layers, and the very detailed fossil, like the shrimp and the jellyfish and the ferns and the tall trees, you know these things don't happen slowly. You see the continuous and sequential layers clearly indicated by what's at the interface, the ripple marks, the little ephemeral bird tracks, and then Mount St. Helens demonstrating this very phenomenon We see coal having to form rapidly with the tree extending through 2 coal seams with many layers in between. Oil, by the way, we can make in 6 hours. Cave formations don't take a long time. Petrification doesn't. What is there about the geologic phenomenon that takes a long time? I love to talk about it. I want to talk about fossils and rocks in terms of the age of the earth. That's my briar patch. That's where I want to go. Love to talk about it. It's all rapid. Now then, why do you think the earth's old? It's not radiometric dating. That's not too good. It's certainly not the geologic phenomenon. That says the opposite. And all we've been talking about so far is the evidence for the old age of the earth, and it really turns out to be the opposite. Let's think for just a minute about some of the young earth evidence, which we haven't really dealt with, as described by anti-creationist W.D. Stanfield. Now, he hates the creationist, written several books of it, but he says, okay, there are some indicators of a young earth, which you haven't heard about probably in the textbooks. He refers to water from volcanoes and lava from volcanoes. And when we learn how much is coming out and how many volcanoes we have, there's some very interesting information there. We've got about 600 active volcanoes in the world today, about 10,000 inactive, which I think is primarily from the time of the flood, but 600 that are now active. If we take Paracotin, which is probably the most studied volcano in the world from down in Mexico, we know how it formed and how much gas is, and most of the gas coming out is the H and the O, the H2O forming water for the first time, juvenile water. Most of it is water coming out, and then of course the lava. But there's enough water coming out that would fill the oceans. 70 of the volcanoes like this would fill the oceans in 1 billion years. They're supposed to have been 4.5 billion. In 600 of them would fill the ocean 8 times. And that's what we have active today, not counting the 10,000 inactive. What are you going to do with all the extra water? And of course, nobody thinks all the water came from volcanoes. 4 of them, with the output of lava that we see at Paracotin, would account for the entire crust of the earth in 1 billion years. And of course, a very small portion of the crust of the earth is from volcanoes. This says it's not that old, which Stanfield acknowledges. When you look at the pressure in oil reserves, we dig down and drill down and we tap some of these gas wells and it'll blow the rig way up into the sky. You've seen probably movies of that. How does this rock maintain the pressure as long as they say it's been there? You can measure the porosity of the rock, which you have to know in order to discover oil, know if the rock can hold the oil. And it's fairly simple calculation when you know the porosity to see how long the pressures could be maintained. There's no way these pressures could last more than just a few tens of thousands of years, but they're supposed to have been there for 4.5 billion or at least billions of years. We can measure very accurately the uranium accumulation in the ocean. Geiger counters, we can really, and we know how much is being delivered to the ocean each year and how much is there. Well, not just a minuscule fraction of what ought to be there if it's been going on very long. Same thing with radiocarbon in the atmosphere that we mentioned a moment ago. It would reach equilibrium in 30,000 years, according to Libby, who got the Nobel Prize for the radiocarbon system. It's not. It's about 20% short of equilibrium. Hasn't accumulated to that point and slows down as it approaches. According to Stanfield, the helium in the atmosphere ought to be at least 50,000 times greater than what it is. Now, since he wrote this, there have been some mechanisms proposed that could possibly explain that, but that's at least questionable. But that's his argument. He says there's the meteoric dust in the strata would likewise indicate a young Earth, and there are no meteorites in the strata. Some craters, maybe, obviously in some places on the surface. But here is this geologic column which records 500 million years of time, where are the meteorites? It ought to collect them all the time, shouldn't it? But if it's a year-long series of catastrophes and just happen quickly, then we can understand there being very few. And we possibly have found a few, but they're virtually none. He says none. Population dynamics certainly argues for a young Earth. When you look at two people at the present population growth rate, from the time of the flood, time of the creation to the flood, you've got 6 billion people at actually less than the present population growth rate. 2,500 years. What happens in 25,000 years? It fits our view, it does not fit their view. And these are the arguments of the anti-creationists. He says this is good evidence, and it is, in each instance. And those, there's quite a few of them. When you look at the evidence for the young Earth, there's a lot of good evidence, even according to the anti-creationist. When you look at the evidence for the old Earth, they're okay. Your radiometric dating and your geologic phenomena, that's not really very good evidence when you look at it carefully. We have more and better on one side of the scales. We have fewer and not so good evidence on the other side of the scales. Now, which is the better model? I think very obviously the best scientific conclusion is that the Earth is young. That's what the scientific evidence, if you just go by the science without the philosophy and the religion, or just go by the science, it fits better. We have more and we have better evidence. It fits the facts best.